And then I'm going to minimize this bar here. Let's put it down here. Okay, can everybody at home see me and see the slides? Okay, we're all back. Okay, and so what we're going to do here is we're going to finish up chapter 10 today and start chapter 11. And with that, we're going to look back at this mechanism of the allylic halogenation. I got partway through it, so I want to start it over because it really makes sense if you start from the beginning. Okay, so in the case of this allylic halogenation, we're not going to add across our double bond. We're going to have our double bond is going to remain intact. So now we have two functional groups. We're going to have the bromine and we're going to have the double bond. But we have to use a special reagent for that. It's called NBS, N-bromosuccinimate. Okay, now the bond itself can homolytically cleave, but it works better with an initiator. So in our first step, we have no radicals, and then we use an initiator to generate our RO radicals. Our RO radicals then can react with our system to give us other material. But what can also happen is the nitrogen bromine bond here. I'm going to start going over here now. The nitrogen bromine bond is also very weak, and it could also break with heat and or addition with heat, so that we can get both of these reactions. We'll do the initiation step of creating the first radicals. Now, the next thing that has to happen is we have to do a hydrogen abstraction. Okay, so our bromine radical or the OH, the OR radical, abstracts a hydrogen at the allylic position. Remember, we don't want to extract the hydrogen at this position because this position would make a vinyl radical. And so we're not going to do it at this position here. It's a vinyl radical and it would be unstable. But it turns out the energy to do the hydrogen abstraction is low enough that we prefer to do that to form the more stable allylic radical. Okay, so we're going to form the allylic radical because it's easier to form the allylic radical than to add across the double bond and give us our non-allylic radical, just our secondary radical. That's the driving force here. We're using our radical formation to form the more stable radical, and that gives us this right here, this allylic radical. Okay, now the next thing that happens is we have with that, we've generated HBr, okay, in the system. So we didn't have it in the beginning, but we generated HBr during the radical abstraction. And when we have HBr, we can now have the nitrogen act as a base. And it can be protonated. And so you end up with 4 bonds around your nitrogen and a bromine as a nucleophile, okay? So in this case, the bromine actually likes to have the bromine-bromine bond. And so it'll actually abstract the bromine from here, leaving the electrons back on the nitrogen to give us a little bit of bromine, diatomic bromine, okay? If we had a whole bunch of bromine around, what would happen is it would add across the double bond. We wouldn't get the product we wanted. So by only having a little bit form after you've already formed the allylic radical, then the bromine is going to react with the allylic radical that already formed. So every time you generate an allylic radical, you generate a little bromine. And then it's going to react with the allylic radical, and it's going to keep going and going and going. So our allylic radical is going to react with our bromine to generate a bromine radical, and that bromine at the allylic position, one off of the double bond. Okay, now, so that's a propagation step. So we can then use this to generate some more allylic radical. And again, we produce a little bit of HBr, which then gets turned into bromine by this reaction here. And it keeps going and going and going. So the allylic radical is there first, and the allylic radical is more reactive than the double bond. Therefore, we get the bromine at the allylic position. Questions on that? Okay, so that makes this reaction very specific to HBr. And it gives you a very specific material in which you have now 2 functional groups. So it's going to become very important as we go on to other chapters to create those two functional groups. All right. So the next thing we have is the regiochemistry of the allylic halogenation. In this case here, because you're generating your radical, your allylic radical, remember it is resonance stabilized, so it has a resonance hybrid. Okay, and in this case, the resonance hybrid spends part of its time over here and part of its time over here. Okay, and when the radical reacts with bromine, we end up having the double bond is now trapped in whatever location it was in that side. So if it attacks here, we end up with a double bond on the inside of the molecule. If it attacks, if it attacks here, we end up with the double bond on the end of the molecule. Okay, so you do have regiochemistry, but look at what clever thing we did up here. Up here, it doesn't matter whether it attacks this side or this side, it's going to give the same product. So we actually use the symmetry of the molecule to generate only one product, where this unsymmetrical product here generates two products. Now, which one do you think is going to be the major isomer? The 1-bromo or the 3-bromo? The 3-bromo is, wouldn't the more substituted double bond be the more stable one? So the 1-bromo is probably going to be one of the major isomers, because it has two substitutions on it. The other has only one substitution on it, so it's probably going to be a little more stable. Okay, but it all comes down to the fact that it could attack at either side of this resonance hybrid. If it attacks here, the bromine attacks here, you get the 1-bromo, and if it attacks here, you get the 3-bromo. Okay, questions on the regiochemistry of allylic halogenation? Okay, so we're almost done with chapter 10, but I'm a polymer chemist, and one of the great reactions that we can do as a polymer chemist is to actually do a polymerization using radical chemistry. So let me tell you about what a polymer is first. Poly means many, mer means unit, so it means many units. Okay, and if you have one of them, it's a monomer, mono meaning one. Then you have two, it's a dimer. Three, it's a trimer. If there's too many to count, you just call it polymer, many mers. Okay, and so the process of actually producing a polymer is called the polymerization. We're making a small molecule into a very long, big molecule. Okay, and so what we can say without that is that, let's say your molecule weighs 100 grams per mole. Okay, if you took two of them together, it weighed 200 grams per mole. If you hooked 1,000 of them together, that would weigh 10,000 grams per mole. That one molecule would be. So these get bigger and bigger. There are actually polymers there that have 50 million molecular weight, grams per mole per individual thing. So these get very big and very large, and it's a very big part of our chemical industry. Okay, so in the case of vinyl polymers, we have a C double bond C, and then there's something else on there. Okay, that Z could be a number of different things, and I'm going to show you a few. And as you change Z, it changes the property of the polymer. Okay, so if it's something big and bulky, you're going to get something tough. If it's something small, you're going to get something rubbery. If it's something like chlorine, you're going to get something that's very different than everything else. Okay, so the Z will affect the properties of the resulting polymer, but the process is the same for all of these. Okay, so the idea here is that we are going to take our little molecules using our radical chemistry. Remember, radicals only do two things: abstract a hydrogen, add across a double bond, generating another radical. So we're going to do that process here because we have double bonds. And we're going to link this one to this. We're going to link this one to this. And it has a very specific way it joins. So if we did that and we drew it out into our line bond drawings here, we're going to see that these Z's are perfectly spaced exactly one CH2 apart. Okay, and it's going to be perfectly that way for most of the polymer. Okay, now why does that work? Well, we're going to be using our radical polymerization, and we're going to use that addition across a double bond that generates another radical. Okay, so the first thing we have to do is initiate. So we have 0 radicals going to radicals. We have our initiation step. Okay, now once we have our initiation step, we can generate our first radical by having it add across the double bond and generates a radical on the more substituted side, the side where the Z is. Okay, well, now we have a radical that can add across a double bond. And so that creates a new carbon-carbon bond right here and another radical. And we can do it again and again and again. And so you're always creating a new carbon bond and then a radical here, new carbon bond and a radical here. And it just keeps going and going and going until you run out of vinyl things to react with, or you get to your termination step. Your termination step is typically having your radicals initiator terminate the reaction, and you end up with that at the end of your chains. Okay, so do you see how this mechanism is exactly the same as the other one we did, but instead of creating just one molecule, one little molecule, you're creating one big molecule. Okay, so it's the exact same chemistry. Okay, questions on the chemistry? Apparently they're grinding something outside. All right, so let me show you a couple polymers and I want to tell you about them. Again, they're all polymerized the exact same way. And this one right here is the most simple would be ethylene. And it would just be this right here. And if you take the ethene right here, or the trade name is ethylene, and you polymerize it, you get polyethylene. Okay, everybody heard of polyethylene, PE? It comes in low density and high density, and it's used for packaging and films and tubs. It's fairly chemically inert because the carbon hydrogen bonds and the carbon carbon bonds are nonpolar. So it can be used for a lot of different things, although it's kind of a little bit plasticky, a little bit rubbery at times. Okay, by changing it and adding just this methyl group here, so we're instead of doing ethylene, we're doing propylene, so it's 3 carbons. Right here, that methyl group changes the properties. And if you have that clear packaging that your scissors come in, and you need scissors to get into the package with your scissors, and it's really tough, that's usually polypropylene. Okay, so it's a little bit tougher than polyethylene, and it can be clearer than polyethylene. Okay, but let's change our Z from the methyl group. Z is a hydrogen here. And so let's change our Z to a chlorine. So we would call this chloroethene, but the trade name is vinyl chloride. Okay, so that means if we make a polymer out of it, it's called polyvinyl chloride, or PVC. Okay, if you've ever been to a hardware store and you looked at that white pipe that they run water through, that's PVC. Okay, that's pure PVC. And it's really good because you can sterilize it because it has the chlorine on there, so it makes it less reactive to the oxidizing nature in bleach. Okay, now if you don't hang out in hardware stores, you hang out in bars. The clear tubing that goes from the keg to the tap, that's also PVC, but it's flexible. What they've done is they've taken it and added a thing called a plasticizer to it to make it clear and flexible, but it still retains its easy to sterilize properties, and it makes it really good for sterilizing your pipes and your thing. So PVC can be used in both of those situations. Okay, now let's say you don't hang out in bars and you don't hang out in hardware stores. Well, if you ever had something where you had something that was, nothing would stick to it. Like sometimes the pans would be a polyfluorinated system. Well, if you have tetrafluoroethylene and you polymerize it, you get polytetrafluoroethylene, or PTFE, trade name Teflon. Okay, Teflon. It's very dense, but it has a very strong carbon-fluorine bond. And the fluorine has its full octet. It doesn't like anything to stick to it. It's very hydrophobic, and things just slide right off it. Okay, slides right off. Okay, but again, they're all made the exact same way with that same polymerization, that same reaction of radicals, adding across the double bond, generating another radical. Okay, so let me talk about 2 more polymers. The top one here is called polymethyl methacrylate. So this right here is an ester with a methyl alcohol group on it. And then this is another methyl group here. Okay, this polymethylmethacrylate is actually used a lot in contact lenses and in windshields because it's very durable and tough. Okay, but notice we're also polymerizing right here. This is our Z right here. And so it doesn't get in the way of the polymerization. Having that tertiary radical still lets it react. And it reacts that head to tail function. So this radical is going to react with this side of another molecule. So we get that perfect head to tail reaction. Okay. So the last polymer here I want to talk about, let me see, I think it's the last one. Yeah. The last one I want to talk about is called polystyrene. So styrene is you take a benzene ring and put a vinyl group on it, and that's called styrene. And you can actually have styrene as styrofoam. Okay. In styrofoam, what they do is they blend it up with water and a blowing agent called isobutylene, and they polymerize it. And so it's in these little beads, but it's got this trapped liquid in it. And then they take those beads and they pour them into a mold. Then they hit it with steam, and that causes the beads to expand, the stuff to boil out of the inside. And so they get puffed up into foam, and then they stick together. That's why if you look at a styrofoam cup, you can actually see little teeny rings on them. Those are the individual beads that were done to make that mold. Okay, so it works really well because it puffs up and then the gas escapes. And now you have a water impermeable thing that insulates because the foam has air in it and the air insulates the heat transfer. But if you don't foam your polystyrene, it actually makes a very tough polymer. And they use it a lot for silverware, plastic silverware. And you know you have polystyrene because if you break it, you can smell it. Styrene has a unique smell, and the polymer decomposes readily back into its monomer state. And if you break the fork, you can snip it, and that's polystyrene. Okay, so these are just a few of the polymers, but they all use that same radical mechanism. Okay, questions on polymers or radicals? Yes.
So we're just looking at the behavior of the Z.
Yes, the Z changes the property. So you go from something that puffs up to something that's a hard film, that's something that's really hard to get into. That's all because of the Z. So, but it's amazing, you make so many different things with the same reaction. Just like SN2, you can make so many different functional groups with the same reaction. Okay, all right, so that's the end of chapter 10. And so I'm going to start chapter 11. And we're going to see, so a lot of this is review from other things, but we're going to start chapter 11 today. And then I will have I'll actually continue with chapter 11 on Friday. I'll continue with chapter 11 on Friday. Okay, so in this chapter, we're going to talk about alcohols and ethers. Okay, so this is the next higher priority of functional group from where we were. Ethers actually are just like chlorines and phenyl rings. They are always substituents, but the alcohol changes the name. So it's higher priority. And so we're going to our next highest priority thing. We're going to look at how to name them and the common names of the alcohols and stuff. Some key molecules that contain these groups. And so we'll look at those. And then the reactivity of alcohols, ethers, and a special group of ethers known as epoxies or epoxides. Okay, so when we're talking about our nomenclature, our alcohol is a primary, secondary, or tertiary based on the carbon it's attached to. So if we had this right here, this is going to be a primary carbon, therefore it's a primary alcohol. Now we need to know this because they react differently, so we have to pay attention to that. Here, this is a secondary carbon. Remember, we're looking at how many carbons are attached to that carbon. And there's only 2 carbons attached to that carbon. Then we have a hydrogen and an alcohol, which makes this as a secondary alcohol. And our last one here has 3 carbons attached to it, so it's a tertiary alcohol. Okay, so notice alcohols are only on sp3 hybridized carbons. Okay, now we do have some, and these are the names for them. If you only have 2 things on it, you're going to have F, right, for 2, and all, so it's going to be ethanol. If you have 3, it's going to be propanol, but you have to say where the O is. And in this case, it's on the 2 position. So that's 2-propanol. And on the third one, the actual IUPAC name would be methylpropanol because it's branched, but a lot of people just call it T-butanol or T-butyl alcohol. Okay. All right. So when we have hydroxyls next to other hybridized materials, they still have to be attached to an sp3 hybridized carbon, or they change functionality. But you can have them one CH2 off, and that will be allowing it to be that true alcohol. Okay, so this one right here is 1, 2, 3, so that's propanol, 2-propanol, and the 2 is for the ene, so that would be prop-2-ene-1-ol would be the better name for that. But it has a special name called allyl alcohol. Remember in the last chapter where we did the allylic halogenation? That was 1 carbon off of the double bond. So allylic means that 1 carbon off. And so this is our allylic alcohol, or our allyl alcohol. Now, if we have a triple bond here, we can actually go with an ine-ol. So it'd be a 2-ine-1-ol, but it has a special name called propargyl. I don't know the origin of that. I should. I used it a lot in my grad school. And then this one right here, because this right here is the benzyl group, right here with the CH2 hanging off there, that's the benzyl group. We call that benzyl alcohol because it has that alcohol on the sp3 hybridized carbon. Okay. Okay. So other than that, we were going to name our alcohols just like we learned back in chapter 2. You have, it's changing the name, so you want it as the lowest number, but you have to make sure you take into account your nature of your carbon. So you still have to do all 4 things, which is your parent, your suffix, infix, and prefix. So don't forget all of those. Now, when we have the OH bonded to a benzene ring, we now have a special group, okay? When we talked about acids and bases, we said phenol had a different acidity than an alcohol did because of conjugation, okay? So that's why they have their own special group, and we'll talk about more next semester when we talk about benzene rings. But this right here, this functionality is called a phenol. Phenyl alcohol, phenol. So if you think about it as a phenyl alcohol, it's phenol. And then we're going to learn how to name these things next semester. But I want to know that this is not a regular alcohol. This is a phenol. They are more acidic and have different reactivities than our other alcohols. Okay. So the next thing we have is ethers. And we have those are, if with the ROR functionality, they lose the hydrogen bonding that our alcohols have. Okay, so that tends to affect their properties. Okay, and we can have a bunch of different ways to do this. And so when they're symmetrical, they're really easy to do because the common names would be something like diethyl ether, because it's 2 ethyl groups and they're symmetrical, so it's easy to say. But what would it be if we were naming it IUPAC? Okay, ethers are always substituents. So that means we have to break the molecule up and say, this is our substituent. So what's our parent? Our parent is ethyl, right? So it's ethane. So we have to name this substituent now because ethane is its parent. And when we have this, we have 2 carbons on there with an oxygen. So we call that ethoxy. Ethoxy, okay? And we're going to call it 1-ethoxyethane, and it all runs together. Okay? So that's the IUPAC name, okay? Because they are always there. So in this side here, which side would be the parent? Which is the longest chain? So the methyl is only 1 carbon. This chain has 3 carbons in it. All right, so if our longest chain is going to be 1, 2, 3, so this is going to be propane. Okay, and now we have substituent 1 into the methyl group and substituent 2 methoxy group. Okay, so we're going to do, let's see, that's going to be 2 methyl, 2 methoxy. And let's see, and methoxy comes before methyl alphabetically. So it's going to be 2 methoxy, 2 methyl propane. Now, if you have 2 vinyl groups like this, this would be, let's see, that'd be ethene. So that would be ethene oxy ethene or divinyl ether. And then here, let's see, if phenol's always a group here, so we're either going to have to choose this side or this side. But now we know the group is phenol, so we might be able to use that as well. Okay, so if we look at the names here, the common names are always just the substituents. So on this one, the common name for this is going to be T-butyl methyl ether. T-butyl methyl ether. Methyl. Wow. I have to write that again. Come on. There we go. All right. Let's try it one more time. T-butyl methyl ether. Okay. So here it'd be phenyl ethyl ether because it's a phenyl group and the ether takes into account the oxygen. Okay, and those common names are on the next slide there. So diethyl and divinyl are because they're symmetrical. Unsymmetrical, you put them in alphabetical order and you put the word ether at the end. If it doesn't say ether on the end, it's not a common name, it's an IUPAC name. If you have some kind of alkoxy part in your name, that's an ether. Okay, so let's finish this with just the nomenclature rules, remembering our nomenclature rules, really. We identify the longest carbon chain that contains the carbon which has the OH on it. Okay, the lowest number of carbon goes to the OH because we've changed the name with OH. If that's your only functional group on there, the alcohol is the parent and therefore ends in OL. Okay, so let's name these right here very quickly. And we're going to go 1, 2, 3. So that's going to be propanol. Okay, are we done naming? No, we have to identify a location, right? So it's on the main chain. So the lowest number we can assign to this oxygen is 2, because this has to be 1, 2, 3. Of course, we can number it the other way and it'd still be 1, 2, 3. Okay, so it's 2 propanol. Okay, so let's look at this one. 1, 2, 3, 4. So we have bute. Okay, but we have 3 alcohols. What happens when we have 3 of something? We call it a triol, right? Triol. And now we have to identify its locations. So this is going to be 1, 2, and 3, because if we name it the other way, there'd be 2, 3, and 4. So we're going to call this 1, 2, 3 dash butane triol. Okay. So if you have 2 of them on there, it's going to be a diol. If you have 4 of them on there, it's a tetraol. There we go. 1, 2, 3 butane triol. All right. And last slide. All right. So in this case here, we again have to have the alcohol in the longest parent chain. Okay. You can find a longer chain, but it still has to be on that parent chain. For example, if we went in this direction here, that would give us a total of 8 carbons, but the OH is not on the parent chain. So we can't choose that one. Okay, so in the case of this, if we went this way, the OH is on the parent chain, therefore that's our parent chain. Even though we can get a longer thing, it's just like with alkenes. You have to have both carbons in the alkene on that parent chain. So that means our parent chain is actually 7. So that gives us heptanol. And then we are going to put the OH at the lowest thing. So that's 2 heptanol. And then our other substituent is a propyl group, and it's on the 3 carbon. So that's going to give us 3 propyl, 2 heptanol. Okay. So this should all be just remembering that how we add that. Okay, so we're going to pick up on naming ethers and on Friday, and then we'll see how far we get. And then again, the following week is going to be asynchronous, and I will have this uploaded to Canvas. Well, I'll have it uploaded to YouTube, hopefully by Friday. So you can have all of chapter 11 on that video. All right, any questions from the group? Yeah. I think your next quiz actually isn't until Monday. So you don't have one, you only have the take-home quiz on asynchronous week. So, and that you just turned that in on Monday as well, but we have an in-class one on Monday. That's on Canvas, and that's correct. Quiz 11. It'll be chapter 11. Okay.
So next week we have a quiz on Monday?
No, it's not next week. It's the following Monday.
Oh, okay.
It's the 28th, which is the same day that the take-home quiz is due as well.
Okay.
Okay.
Thank you so much.
All right. Bye.
Bye.
All right. Let me just stop sharing and stop recording. Stop sharing. And